Hello, and welcome once again to our third and final installment of this binational seminar between the National Autonomous University of Mexico and the University of Nottingham. My name is Ana Elena Gonzalez, and I'm very happy to welcome you all to this third session. On this occasion, we are joined by Mirko Magnini and by Jorge Ferrer, from our two universities. I have to say that due to special circumstances, Dr. Daphne Gaviria will not be able to join us on this occasion, but will. And now, just to remind you that we will watch the presentations, and then afterwards there will be time for a Q&A session. And I'm very happy to welcome, as chair for today's session, David Octoloni. Please, over to you, David.
Thank you, Ana Elena, and welcome everyone to this UNAM Nottingham Aerospace Engineering Binational Seminar. I'm very pleased to be here. I am David Octoloni. I'm the Associate Director for Global Engagement at the University of Nottingham, and my responsibility is to work with colleagues across our university to provide opportunities for international engagement and to drive the University of Nottingham's international strategy. And this, the third in a series, is a really important pillar of our internationalization objectives at Nottingham. The pandemic has helped us in some ways. It's been an awful 2 or 3 years for all of us around the world, but the advances we've seen in technology enabling us to collaborate around the world means that we can put on seminars like this, and we can gather academics from around the world together to talk to one another about the important research that they're undertaking. And we're hoping today that this series of talks is the first step in a deeper collaboration between our two universities. We hope that it will lead to not only further collaboration in aerospace engineering, but also to future series in other areas of expertise, and we'll really work together as two universities to try and do this. I'm delighted to be here. I'm really excited to hear what's going to be presented to us today by our two speakers. On behalf of the university, I would of course like to offer my sincere gratitude to Professor Ana Elena and Dr. Daphne Gaviria for all of the work they have done to ensure the success of this series. And it has been successful. The feedback that's come through to us at the University of Nottingham has been overwhelmingly positive. We're really pleased to see the level of engagement from academics here in Nottingham and with you in Mexico. So I'm really looking forward to seeing where this goes. So without further ado, I'd like to introduce our two speakers today. Ana Elena has already introduced them. So Mirko Magnini and Jorge Ferrer. It's really great to have you here, and we're really looking forward to hearing from you. So Mirko, if you could start, please, with your talk on numerical simulations of boiling flows with OpenFOAM. That would be great. Thank you.
Thank you, David. Thank you, Ana Elena, for the introduction to all the session. Let me see how to share screen. And full screen. Can anybody tell me if you can see my slides all right?
Yes, we do.
Okay, thank you. Okay, let's start then. So welcome everyone who is attending this session, and my name is Mirko Magnini. I'm from the University of Nottingham, and in my talk I will present a little bit of the work we've been doing in numerical simulation of boiling flows using OpenFOAM, and OpenFOAM is a quite popular now open source software to run computational fluid dynamics simulations, but not only, as I will show. So the talk has general background is heat transfer and fluid mechanics. So you'll need a bit of this to be able to understand what I'm talking about, but I hope it can be useful and enjoyable for people from the wider background. So what's the general outline of my talk? I will start with explaining why boiling flows, who cares about it, why OpenFOAM, so why do we need an open source solver to do this kind of simulations. I will introduce the boiling solver that we are using, that we developed ourselves, show you how to do validation of these numerical methods for flows that are quite complex, and then I will jump into how we used it for the specific objective of helping the design of micro evaporators. So let's start with why boiling flows. So you may be familiar with the fact that over the past decades, the trend of the the trend of the design power of microprocessors is increasing quite exponentially over the years. So this is a graph that shows a few features of microprocessors over the last 50 years. And if we look at the typical power, the red points, the typical power is really the power that has the processor, which, as you may know, by Joule effect, this power will be dissipated in heat that we need to remove from the system to maintain the CPU, the processor, at a constant temperature. And the heat is now approaching something like 100, 1000 watts. And for example, if we consider the workstation we are using to run our simulations, it's quite an old workstation, but if you divide the thermal design power, which is the, let's say, the heat generated by the CPU, 280 watt, by the size of the CPU, 74 millimeters square, you get a heat flux, which is on the order of the megawatt per square meter. So you can imagine a square meter, and there will be 3.8 megawatts to be dissipated through this small surface. If we take the CPUs used by the UK's tier 1 supercomputer, we have very similar thermal design power and size, slightly lower heat flux. Just to put everything in perspective, the energy flux on the sun surface is 64 megawatt per square meter. So we are not that far. We are maybe between 15 and 20 times below the energy flux on the sun surface. So you can imagine that there's quite a lot of power, quite a lot of heat to be dissipated from these systems. Now, how do we dissipate heat usually? The mainstream method is to just blow cold air over the CPUs. So you have a certain fluid, for example, air, flowing through the motherboard, and the fluid will enter at a certain temperature, which is the, let's say, the air temperature where the computer is placed. And thermal engineers, they typically evaluate the thermal performances of a cooling method in terms of heat transfer coefficient, which is the heat flux to be dissipated, and this we know it from the system that we want to cool down, divided by the wall temperature of the system minus the fluid temperature. So let's say that the wall temperature, we can set it as something like 60 degrees C, which is the max, let's say, it's the standard operational temperature of a CPU. We don't want the CPU to go above 60 degrees. And the air temperature is, let's say, 25 degrees, maybe a bit less in the UK. So if we consider 1 megawatt per square meter, we need to achieve a heat transfer coefficient of 25 kilowatt per square meter Kelvin, which is very large for air, for like air blown by a fan. So one technology that comes in help is to use microchannel heat sinks. So instead of having air blown over the CPUs, we can place these small heat exchangers with many parallel channels. Having many parallel channels enable us to have higher heat transfer area. So we can actually decrease the requirements in terms of heat transfer coefficient, but having a higher heat transfer area. And we know from thermofluid classes that the heat transfer coefficient can be estimated as the product of a Nusselt number, which is a non-dimensional number that tells us how good we are exchanging heat, and the ratio of thermal conductivity of the fluid, which is a property of the fluid, and a length scale. The length scale is a length scale that characterizes the size of these tiny channels. So smaller channels enable us to get higher heat transfer coefficient. And this is the reasoning why, this is the reasoning behind the use of these very small channels. Now, if we consider, okay, we have these microchannel heat sinks, which have very high heat transfer area. They are small, so by nature, we increase the heat transfer coefficient. But there is a limit on the Nusselt number that we can achieve. So this graph here shows Nusselt number versus aspect ratio of the channels. So aspect ratio is like, you can imagine the cross-section of the channel, and we are looking at the width over height of the channel. You see here that we can range the aspect ratio from very narrow channel, let's say very narrow and vertically oriented channels, to very narrow and horizontally oriented channels. But whatever we do, because it's a very small channel, the flow will be laminar and the Nusselt number is limited. So there is a technical limitation on single phase liquid cooling, which is Nusselt number is the best you can achieve is 8.24. And this will put a limit on the heat transfer coefficient that you can achieve. So here two-phase cooling comes in help. So two-phase cooling, we, instead of cooling the microprocessor with, let's say, with water at 20 degrees, we bring the fluid close to saturation temperature. And when the temperature goes above saturation, the fluid will boil. It will generate bubbles. And this boiling fluid is very effective in actually removing heat. So here there is this series of images that shows that a two-phase flow pattern will move from a bubbly flow with many tiny bubbles being generated, slug flow where you have all these long vapor bubbles that occupy the entire cross-section, and eventually annular flow when you get into higher fractions of vapor in the channel. And when we consider slug and annular flow, the theory tells us that the heat transfer is related to the liquid film thickness. So these long bubbles, they all trap a layer of liquid around them. So this is a cross-section of our channel. There will be the vapor at the center, the liquid around it, and we can actually solve very easily the one-dimensional heat transfer through this liquid film. And this is like an ER2 thermofluid class. You can actually find that the heat transfer coefficient that the two-phase flow will enable can be estimated as the ratio of thermal conductivity of the liquid divided the thickness of the liquid film. So potentially we can achieve very, very high Nusselt number if we have a small film. At the same time, if this liquid film dries because, for example, it evaporates completely, then we will lose a lot of heat transfer because there will be vapor in direct contact with the surface. Vapor has a very low thermal conductivity, and then we are doomed. The way these multi-microchannel evaporators work is that because we use a dielectric fluid, we can place the multi-microchannel evaporator in direct contact with the surface to be cooled down. So we get a very, very low thermal resistance this way. So this is the reasoning why we want to use microchannel two-phase cooling. But when we look at the literature, there is quite a vast literature experimental about the microchannel design. But when you look at the literature, especially when you look at the aspect ratio of the channels, you can find a bit everything and the opposite of everything. So everyone, you will see people that say low aspect ratio channels are better, other that say high aspect ratio channels are better, other again that say aspect ratio 1 is the best one. So the study I show you today is oriented to find what's the best microchannel configuration. But why did we use OpenFOAM to do these kind of simulations? Well, you may be aware of people working with thermofluids, maybe using ANSYS Fluent as a commercial software to solve these kind of problems. It's a few years that we transitioned to OpenFOAM for the main reason that OpenFOAM does not need any licenses. So you can run it over hundreds of computational cores without any license. It gives you complete access to source code and it's totally customizable. So especially when you need to use it for research purpose and you want to implement sophisticated models, having full access to the source code is really crucial. And I know that the first obstacle is always that I don't want to install an open source software. It requires a Linux operating system, it's very difficult to use, and so on. Well, I have designed my own OpenFOAM training that is publicly accessible at this link. And I have all a series of tutorials to learn how to use it. It's already installed in a virtual machine. You don't need to bother about installing it. It's already available there. Okay, so this is the only slide with a lot of equations, just because I need to introduce what's the solver that we have developed to solve this kind of problems. So we are solving both the fluidic region of the channel and the solid regions of the channel. For the fluidic regions, we solve the continuity equation. So it's fluid flow and heat transfer. We need to solve continuity, momentum, and energy equations. So we have continuity here. We have momentum equation is the third equation you see here. We have the energy equation. And you see this extra alpha equation here. So we want to solve a multi-phase flow and we want to see the bubbles. So we need an extra function that characterizes where is fluid 1, where is fluid 2, so that we will be able to locate the interface between fluid 1 liquid and fluid 2 vapor by the changes in this variable. So the method we use is called volume of fluid, VOF, and alpha is equal to 1 in fluid 1, 0 in fluid 2, and has values in between in cells that are cut by the interface. So we need to solve this extra transport equation to advect the interface and be able to see our bubble moving. We solve the heat conduction equation in the solid, and all the color-coded red terms in the equation here are the mass transfer term due to evaporation, and we model them using a popular phase change method where the mass transfer is proportional to the local interface temperature. This nice video you see here on the right, it just shows one of the typical test cases where we have a bubble growing in an infinite liquid, and we compare the bubble growth rate with an analytical solution for this problem. Now, how do we validate these kind of models? So we have done a long series of validations, but here I'm just showing you two limiting cases. One is called nucleate boiling. Nucleate boiling is the situation in which we have, like in a pot of water, where we boil water, for example, to make tea, and we see that many bubbles are generated in the water. So here we have a wall at a temperature above saturation. So for example, we have a wall at 112 degrees Celsius, and above the wall there is water at 1 atmosphere, so it will boil at 100 degrees. A vapor bubble is generated, the vapor bubble grows over the surface, and as it grows, it removes heat from the surface. You see that there is this cold ring underneath the bubble here. So we have done this simulation here to compare with experiments, and we compare the bubble volume over time with the experiment. We get a reasonably good agreement. Beyond that, now this is a bit more complex, but we are comparing what happens underneath the bubble. Underneath the bubble, there is this very thin layer of liquid that is trapped between the growing bubble and the wall that is fully captured with a mesh. And the experiments we are using for benchmark, they are giving us the wall temperature as a function of space. X here is the horizontal coordinate. And we can compare our simulation with the experimental result where we get the temperature as a function of X, and we see that in the region occupied by the bubble, which is called microlayer region here, we get an excellent agreement with the experiment. The second set of experiments with which we are comparing is more pertinent to the flow we want to study, which is flow boiling in a microchannel. So we have a small channel, which this time we have water pumped into the channel. The wall temperature goes above saturation. A bubble will grow and will also move downstream because of the flow of liquid. So we have taken an experimental database from the literature where they measure the bubble volume over time. And here we can, on the top right here, you see a video that represents the simulation we are running. And again, we compare the bubble equivalent diameter versus time between experiment and simulation. everything works quite nicely. And so this made us conclude that we have a quite robust numerical method. So after this, we started to work on the study that we wanted to achieve. So we wanted to study the impact of the aspect ratio of the channel. So let's say width over height, the way we define it, on the boiling dynamics and on the heat transfer generated by the two-phase flow. So we start with a long channel with the walls around it. We put symmetry boundary conditions on the sides to emulate the presence of multiple channels. We give a constant heat flux at the bottom wall, and we first run a single phase simulation until steady state. This is the first step. We let the fluid flow develop until we reach steady state, single phase. Then we see the tiny bubble, which is this gray bubble that you see here. And we let the simulation run until the bubble reaches the end. At the bottom wall, we set a constant heat flux of 100 kilowatt per square meter. And we have performed the study considering water at 1 atmosphere as the operating fluid, an hydraulic diameter of 0.2 micrometer. We've also studied the effect of the lateral walls. You know, all these parallel channels, they are separated by a thin wall, and this wall actually has an impact. So we have also studied the impact of the thickness of this wall. So just to give you an idea of how the simulation works, here we will see a video where we start with this tiny bubble here. The wall of the channel, this is the bottom wall. We have the left wall. The right wall is clipped to be able to see within the channel. And on the middle image here, we will see the inner side of the channel to see how the wall temperature develops. On the bottom image, we will see the outer surface of the channel. So as the bubble starts growing, the bubble will grow to occupy the entire cross-section. And when it touches the lateral walls, it generates this contact line on the lateral walls. And you can see that the contact line, the point where the bubble touches the wall, is very effective in cooling down the wall. We can see this ring being developed where the wall is cooled down by the evaporation phenomenon. What we do eventually is to run all our systematic analysis, extract a lot of data from this kind of simulations, and then process them to derive useful quantities. So for the sake of time, I will just skip all this part here just to get to the final point where we have, for example, a situation here where we estimate, well, let's say from our simulation, we calculate our Nusselt number at the wall. So here we have Nusselt number at the wall if average over the entire walls of the channel at the last moment where the bubble touches the end. We have 3 representative aspect ratios shown here. 0.5, which is a vertically oriented channel, 1, which is a square channel, 2, which is a horizontally oriented channel, always heated from below. And here we see how the Nusselt number changes as we increase the aspect ratio. There is a sort of monotonically increasing trend of the Nusselt number. And this is done with the smallest thickness of the lateral walls that we studied, which were hydraulic diameter divided by 8. When we consider much thicker walls, so you see here the lateral walls are evidently thicker than what we had before, what happens is that we have a much larger Nusselt number. And this happens because I had to skip all the slides, but this happens because the walls are hotter. The bubbles grow more quickly and they leave a thicker film of liquid at the wall. Thicker film of liquid means more resistance to dry out, better heat transfer, even though the trend is no longer monotonic. So we can run as many simulations as we want, but it's very difficult to extract a general trend out of these simulations. We cannot give just a straight answer which aspect ratio is best. So what we do with all this data is to develop one-dimensional heat transfer model, which is something that we are doing in the meantime. So we model our bubbles with simplified geometries. We take the heat transfer coefficient given as average of what happens in the liquid regions, what happens in the dry regions of the bubble, what happens in the regions with the film. And eventually we compare our heat transfer model with experiment, which is what we have done a few years ago, but for circular channels. And the comparison with experiment is finally the judge to tell us if we have done a good job or not. So just very quickly for a conclusion, the advantages of using this open source method is that simulations, they run in our specific case on 256 cores in parallel with no licenses. You need some programming skills to use or at least to develop your own solver. We have validated everything with benchmark cases, and we are now drawing our conclusions on which aspect ratio will improve heat transfer, and all the simulations are useful to generate data for model development. That's all from my side. I'm very happy to respond to your questions if you have any, and thank you for your attention. Are you still there?
Yes.
Okay, good. I wasn't sure if I was still connected or not.
No, yes, you are connected. Actually, I am not which will be the order, if we should proceed with some Q&A or I don't know, but
Yes.
I think that would be
Yes.
sensible. Do you agree,
Yeah.
Anna Elena?
Yes, of course, yes. We're going to have some questions for Mirko, and then we go over to your presentation, Jorge. Thank you. But you may ask the questions yourself, Jorge, of course. Yes.
oh yes,
And
yes,
if
yes,
you
yes.
could turn on your camera, please.
Yes, sure. Sorry.
And we also have a couple of questions in the chat as well.
Excellent. Hello, everyone. Yes, I more than questions, I have some comments about Marco's presentation. I think it was really interesting. The fact that he is saying about the problem of using a commercial software instead of open one is really a critical one. For example, for us, we're trying to use some software, but the problem with our problems, sorry for this word, is that, for example, we notice that ANSYS has some issues related with solving some heat transfer problems in space, and this fact was so complicated even when we try to simulate, for example, the thermal environment for satellite. And I don't know, Marco, if you have some issues or some comments about how to simulate, for example, if you have the satellite in the space and you know that there is not convection, that you have only radiation and conduction. If you try some problem like this, or you have some idea how to tackle with OpenFOAM?
Yeah, sure. Well, first, let me say that I used ANSYS for 10 years, and actually, I was studying boiling flows with ANSYS during my PhD. So I've been using for the same number of years ANSYS and OpenFOAM at this point. So I know a little bit of the capabilities of ANSYS and the limits. So the problem, for example, of ANSYS is that the energy equation that it provides, you cannot delete some elements, some terms. For example, if you don't have heat convection, you would like to cut out the convection term of your energy equation, but with ANSYS you cannot do that. What you could do is to solve a new scalar equation that you can do with ANSYS, and then that if you solve a new scalar, then you can cut out the convective term. But you would need to implement everything yourself, let's say. Then if you want to implement radiation, then it's not that straightforward to put the boundary conditions. The advantage of OpenFOAM is that you have full access to the equation, so you can write the equation yourself, but you don't need to code it, at low level. You can solve a new equation with OpenFOAM, just adding the temporal derivative the convective term or not add the convective term at all, the diffusion term, and any source term. And you have full control on how to discretize those terms or to create new boundary conditions, which I think is one of the limits of Fluent. You cannot change the boundary conditions that are available there.
Exactly.
But with OpenFOAM, you can do that. And for example, for radiation, you can already, the nice thing is that there are already solvers of OpenFOAM doing radiation. So you can, for example, create a brand new solver on your own, and then you simply copy paste the libraries for the boundary conditions of radiation in your new solver. And you don't need a C++ expert, because OpenFOAM has these two levels of programming where you have a higher level where you don't need to be an expert of C++, but you can like mix and match libraries. And there is a lower level where, okay, then you need to, if you want to code something very, very complicated, you need to be knowledgeable of C++ to then code something extra. But if you want to use anything that is already available there, you can just mix and match and compile a new solver that I find very, very useful.
And for example, Mirko, I have another question. For example, I really love your research because it reminds me my dissertation topic. And in particular, did you ever try to include for your thermal model a new kind of material such as graphene? Because, instead of, semiconductors and other computer, they're based on some copper material, right? So if you include some graphene, over some transistor devices, so on, the theory said that you will increase the thermal conductivity. But in practice, this is really difficult. I read a couple of papers that they are trying to do this already, but I don't know if you are trying to do this in your simulation or in your research.
Well, let me say that in my simulation, that the material, there are two levels of complications, let's say, for including the material. I'm only at the first one, which is I'm simply solving a heat conduction equation for the solid. So I can put any properties that I want, which means that if I want to use graphene as a solid, if I know the thermal conductivity, the specific heat, and the density, they are just input parameters for me. So that will be very simple, very quick and easy to put it in. And for example, I showed you the result with copper, but I've done them also with steel, aluminum, and silicium, which is a very used material for these microevaporators. So from this perspective, we can simulate anything. But there is a second level of complication, which is actually not tackled at all in my simulations, and it's difficult in general, which is the fact that different materials will have different roughness, and the roughness will impact the nucleation of the bubbles and the way these bubbles can slide over the surface. And this is a very complicated aspect because you cannot solve it at the continuum scale, because you really need to go down at the nanoscale to understand, how the fluid and the material are coupled. And this is something we cannot yet do at the continuum scale in a CFD simulation. We need to find a way to merge molecular dynamics and CFD. So just to answer to your question, in a nutshell, we can input any other material, but only from a point of view of heat transfer performances. If we want to go farther, then we need a bit more physics, but we need more clever people than myself to do that.
Yes, no, don't say that. It's really interesting,
Thanks, Jorge.
I think that, and thank you. I don't want to take more time with others.
Okay.
Thank you.
Thank you. We have a question in the chat from Raul Santos, and my degree was in geology, so a lot of what you said has just gone completely over my head. So you may have already answered this question, but the question is there a fluid other than ammonia for thermal management in space environments?
You catch me off guard. I'm not an expert of which fluid they use for thermal management in space environments, which is a shame because I'm also part of ESA, of the European Space Agency, with expertise in heat transfer for space. So it's really shameful. I believe that aren't there other fluids, for example, I think also other dielectric fluids are used for space applications, not only ammonia. So something like R245FA, so some other, like, I don't know how they're called, like hydroolefins. I never remember their names, but there is a vast variety of fluids, the electric fluids used in the computer industry, which I believe should be okay also for space applications. I don't know if we're restricted to ammonia. So just to answer the question quickly, I believe there should be other fluids other than ammonia for space applications.
Fab, thank you. And I think you've answered this question with your talk about open foam and the training and the systems and so on. But
so if I see Luz Betty, I see her question here. I can provide the link. Actually, I can put it here in the chat after my talk. And I have these tutorials online, and there is a lot of material already there. I have a long slideshow with all the exercises and a lot of extra links with extra material that can be found online. There is a lot online already available. You just need to know how to find it, and I can help you with that.
Amazing, thank you. Does anyone else have any further questions before we move on to Jorge's presentation?
I see another question of the chat. OpenFOAM can simulate magnetohydrodynamic fluids. Yes, there is already, I believe, a module to do that. Otherwise, you can easily implement your extra equation within one of the existing solvers.
Great, thank you. Anyone else?
Thank you, David. Thank you, everyone else, for the questions.
No, thank you for your presentation, and thank you for the questions and discussion.
My pleasure.
Amazing. Okay, thank you. So Jorge, over to you. You're on mute.
I'm sorry.
We cannot hear you. There you are. There you are. Okay. Good. Thank you.
Thank you. It says that I cannot share my presentation.
Can we? Fix
Sorry,
that?
you can. Yeah,
Ah,
he can,
okay.
sorry.
You should be able to, yeah.
Okay, let me try again. Perfect. Can you see the presentation?
Yes, we can.
Yes, we can. Thank you.
Hello, are you there?
Yes,
Yep, we're
yes,
still
we can
here.
hear you and we can see.
Okay.
Okay, thank you so much. Well, first of all, thank you for the opportunity.
Your audio appears to have dropped out, Jorge.
What can I do?
Yep, there we go.
Right now?
Perfect.
Excellent. Thank you so much.
Sorry for this technical inconvenience. Okay, first of again, I really thank you for the opportunity for being here. I really enjoy Mirko's presentation. You are doing a really nice and fine job, and for my particular view, I really will look forward to keep talking about these numerical simulations. Well, for the time being, now I will present you an initiative that we are carrying since 2014 at the School of Engineering, that is the National Laboratory of Space and Automotive Engineering. This is a dedicated facility to develop automotive and space systems. So, first, it's necessary to understand what is our natural ecosystem or natural environment. The National Laboratory is part of the School of Engineering. The School of Engineering at UNAM is really old. It has already 230 years of history. And so far, the population of the school is around 13,000 students, so it's a really big school. We have operations in different states, not only in Mexico City. Mexico City is the main campus, and the School of Engineering has operation in Mexico City, in the state of Morelos, state of Nuevo León, and the state of Querétaro. And I am marking here where the state of Querétaro is. The start here is indicating the main campus that is in Mexico City, and Querétaro is here, is around three and a half hours north west Mexico City. And here in Querétaro, we have two departments, the Department of Automotive Engineering and the Department of Aerospace Engineering. And at the right, you can see a part of a sample of research fields is related with mechatronics, vehicle dynamics, mathematical computational modeling, some plastic characterization, noise and acoustic vibration research, some research devoted to EMC, thermofluids, and embedded systems. The idea of this unit, that is the Advanced Technology Unit, that is part of the School of Engineering, is try to have some more deep connection with the industry located here at the center of the state. And of course, when you talk with the industries, they will share with you some of these particular problems that they have. And for us, it's really important to try to understand them in order to have to create these partnerships. No, and this is an important to share with you, because sometimes the companies want to have some they want to contract some particular services, such as to measure a particular variable, to try to run out some test and so on. But for us, it's more important to try to create these partnerships in order to be side by side, to try to tackle some of their problems. And with this, we want to create some long-term relationships. As you can see, now we are seeing some of the some peaks of the main building of this of this facility. It was constructed with an industrial idea. We have several laboratories inside, as you can see. And the most important thing is to understand right now what is a national laboratory. And this is really important because the government of Mexico invested a lot of money trying to create a dedicated facilities going from physics, chemistry, some applying science like nanotechnology. Also, they're including some humanistic and linguistic centers to perform some research related with social sciences. And the idea of these facilities is to be unique here in Mexico. The idea is that they don't need to repeat the facilities. Only to be clear, CONACYT stands for the National Council of Science and Technology. It's a branch for the government of Mexico. And knowing this, this particular program wants to tackle 5 different aspects of the environment of Mexico, such as academia, government, society, industry, and the environment. And they call this kind of set of interaction some critical, because they wanted to focus all the resources for some social social aspect of solving national problems. So in knowing this as a background, the National Laboratory of Space and Automotive Engineering is the only facility here in Mexico, dependent of this national program, to try to foster the design, integration, fabrication, and test of automotive and space systems. Since we are talking right now about aerospace engineering branch, I will take aside the automotive aspect of this laboratory. However, we can talk more in maybe in a different talk or in a further meeting. At the bottom of this slide, you can see some interesting things when you can learn more about some details about the laboratory. So far, this laboratory has these 2 departments, aerospace and automotive engineering, and I will talk only about the aerospace laboratories related to foster the space technology. We have aviation labs, and a space propulsion and thermal vacuum lab, an electromagnetic compatibility lab, an embedded system lab, software and hardware in the loop lab, and a ground station. And it is necessary to point out that in Mexico, the story of our nation is kind of young, since our space agency was created around 2010. It is not old, and we are trying to not buy a commercial system or an already made system. We are trying to create our own solutions for our national problems. So from this point to the end of the presentation, I will take you for a very quick tour about our facilities. And this is important to mention because in a previous talk, we know that we don't have a bunch of projects like you have, like the University of Nottingham. They are really interesting and really pertinent. And from our side, we are trying to try to foster new projects, and in particular, we are trying to cross these initiatives with the facilities that we already have. For example, for the vibration laboratory, we have several shakers already located here. As you can see, this is a traditional vibration lab. However, one of the key features of this laboratory is the equipment that you have in the top of the slide. That is a vibrometer. This vibrometer is an interesting equipment because you can measure in real time the deformation of any sample that you are trying to test in a traditional shaker. And this is interesting because the measurements are made without contact. So you can so basically you need you can take away all the cables or the sensors because they induce some additional weight into the measurements. And with this equipment, with the vibrometer, you can take off account of all the calculation and see in real time what is going on with the sample. And with this, you can try to detect some interesting points and see if they will work with the vibration or you need to reinforce. And of course, with the aid of numerical simulation, you can do a very good job trying to foresee what will happen with the system that you are developing. For the point of view of airspace field, we're using this to perform the vibrational test to the CubeSats. Our idea of the facilities that we created, that we projected, was to perform and develop microsatellites. However, we know that microsatellites are more expensive than nanosatellites. So for this reason, we're trying to use all the equipment for CubeSat. However, they are prepared for a microsatellite size. The other equipment that we have in other laboratories is space and propulsion laboratory. This facility is really interesting also because in the entire nation, we don't have environmental tests for the thermal and vacuum chamber. The vacuum and thermal tests. For example, as you can see here, this is the only chamber of these dimensions. It has a 2 diameter wide times 3.5 meter long. Is a really big chamber. As you can see from the perspective, we have some of the researchers that are using the chamber, and you can see the size of this equipment. The chamber is embedded in a in a clean room. As you can see, here is the entrance of the chamber, and the idea is to have all the entire process to integrate the elements here in this table, and after for example, the satellites on or maybe some electronic card or so on are finished, you can introduce here in a controlled environment, and then you introduce this sample into the chamber. You close the chamber, and from the outside you can run the test. As you know, these tests are really long. The duration is around from 4 hours up to 1 month. So the interesting fact of this laboratory is, so far as we know, is the only facility with this with the capability to reach a military standard, and we are trying to reproduce some standards from other parts of the world, such as the Kyushu Technological Institute, that they have a very nice state-of-the-art environmental laboratory. And with this, we are trying to create a site here in Mexico where a community from academia or maybe industry can bring our projects, bring our tests, and basically try to study here how we behave under vacuum and thermal conditions. An interesting thing here is that this laboratory is called also a propulsion laboratory because we're trying to develop our own thruster, in particular Hall thruster. The graphic that you can see is a very nice block diagram where you can basically the idea is to try to share with you clearly what is a propulsion system. And this is important because so far we are the only university that are developing space thrusters. And in each of these blocks has some titles, and in particular, we have here the mechanical structure that will hold all the satellite elements. Of course, there will be other elements involved. However, the electric propulsion of the space propulsion system that we're developing are made of three different parts. One part that is developed to introduce the propellant, other part that controls the whole thruster, and of course the thruster itself. And the thruster itself has been a really hard task to perform, because as you know, there is some of the materials required for the whole thruster that are also used for some military purposes. So we are trying to, when we bought some of these materials, when we acquired them, we need to fulfill, well, first of all, we need to figure out who is selling this material, and then trying to buy it, showing that it will be for some academic purposes. Of course, the whole thruster is the oldest thruster available for space purposes. This is a very quick diagram. It's trying to show how it works. And in particular, we need to have in account that the thruster is divided into particular parts. First of all, a main part that is called the thruster, another that is called the cathode. Basically, the main idea of how it works is the following. The cathode will emit some electrons, that these electrons will be captured at the top of the thruster by a magnetic configuration. It can be some magnets, or it can be some copper coils. And the idea is that the electrons will be confined in the top in a very crowded cloud, and they will spin in the top of the whole thruster. And in the other side, the thruster will receive some propellant from the outside. This the propellant is can be xenon, argon, or other gas that is neutral. However, when this material with this gas encounters the electrons that are already spin, they will start to have some collisions. And since the energy of the electrons is really high, they will start to remove from this neutral gas electrons for the top of the layer of its electronic configuration. Therefore, they will form an ion gas. And with a combination of electric and magnetic fields, that this ion gas will be exposed or can be directed outside the thruster. And with this movement, the thruster will feel a force in their magnetic elements, and with this, the satellites will be moved. And for us, was really difficult to try to figure out how the thruster will work, because, of course, in the literature they will have they will mention them like the basics of how it works. However, they won't tell you the details. So at the end, we are trying to reproduce to have our own device here in Mexico. We already have a patent of the whole thruster. We're already working in the third version of this thruster, and the idea is to perform the test in the thermal vacuum laboratory that already showed. The other laboratory that we have is that ENC laboratory. Here in Mexico, we have only three of sorry, let me think. We have three of these facilities, and as you know, depending on the kind of the standard that we want to fulfill or that we need to fulfill, it already impacts how the laboratory needs to be projected. For this particular case, the laboratory was projected to fulfill the military industry, to fulfill automotive industry, aerospace industry, and also electrodomestic industry. The size of the EMC lab is around 7 by 6 by 4 meters for the internal dimension, and the external dimension is 7 by 7 by 5. So it's this square room that you have here. And the interesting thing here is that this is the only EMC chamber in Mexico that can you can introduce a small car of 3.5 tons of weight. And this will give you the opportunity to test some of these new kind of communications and entertainment system that the automotive industry is trying to foster worldwide. Of course, all of the systems that we are developing, they need we need to create some electronic cards, not some PCBs elements, and we have already the integration line to create these devices. We know that so far today, you can basically design your own system, your own card, and you can send it out of Mexico, for example. They send to China or other very accessible country where you can pay to manufacture the system that you are sending to them. However, this can give you some headache, because at the end the industrial property is not guaranteed. However, here, since we are creating our own PCBs boards, really we can secure that all the intellectual property can be secure and protected. And other thing that it is good to know is that we have a real nice real-time simulator, that is the OP 5600. Is really interesting to know that with this we can emulate automotive and aerospace systems. And in particular, we already use this to simulate the internal pressure of the cabin in an airplane. Of course, we already have some simulations about the satellites that we're developing, and this is a nice nice thing to mention, because at the end we have numerical simulation. We have this for real-time emulations. At the end, we are trying to construct all the loop in order to perform all the required simulation that we need before manufacture the system that we need. Of course, we have ground station. This is compounded by 2 antennas. One is a dish antenna, and other is a VHF antenna. Professor Alberto, I understand that they talk a little bit more about this facility. And the interesting thing here, again, is that these antennas the combination of these antennas are unique in Mexico, because so far is the only ground station that can track low orbit satellites. In Mexico, we have really state-of-the-art facilities, but they are dedicated for GPS signal receiver and so on. They are only receive, no send commands, and this ground station, it can do this. Of course, it is important to mention that we have not only the facility, but we have some projects where we're using the facilities. One is Nanosatellite Auto that Professor Rafael already talked about this initiative. And I don't want to repeat things that were mentioned before, but I think that is really interesting because at the end, this is like our example case that our facilities are in good shape to perform this kind of tests already in Mexico. Other thing that is interesting to mention is that in 2020, we submit a really interesting project to create a new academic program, that is the Aerospace Engineering Program in Mexico City. This is a very interesting program because at the end, the duration of this bachelor degree is around 5 years. And at the end, the student will choose between two cores of knowledge. One is aeronautics, another is astronautics. And with this, we're trying to fulfill one of the principal needs that the country already have. The industry wants to have a very high-end specialized engineers. And the problem is that not in Mexico, we don't have all the critical mass to create a bunch of good engineers. However, with this, we're trying to put the elements to create the critical mass that in 5 years we can offer a very good engineers to be integrated in the industry. And last week on Wednesday, recently we received the good news that this academic program that is already offered in Mexico City will be offered in Querétaro, where is the ENES Juriquilla, where is the National Laboratory of Space and Automotive Engineering. And with this, we are trying to close the loop to create a very good professionals, to have very good facilities, and also to have a high impact projects. With this, I'm hoping not to be very long presentation. It's really an honor to share with you what we are doing. Of course, we need more time to consolidate this initiative, where I really believe that we're in the correct track. Thank you very much, and I don't know if you have some questions, concerns.
Thank you very much, Jorge. Yes, opening it up to the floor for questions. I can't see anything in the chat, but I don't think my chat is working properly. So if Ana Elena, if there's something in the chat that I can't see, please do say.
I don't think so. We don't have any questions yet, but since I unmuted my microphone, I would like to thank both speakers. I think they were both fantastic and so open to exchange, which is what we really want to create, you know, this type of dialogue. And so yes, congratulations to Mirko and to Jorge.
Thank you. Yes, wholeheartedly agree. Many thanks to you from us here at the University of Nottingham.
Can you hear me? Sorry, it's Mirko.
Yes, we can hear you.
Yes.
I think that someone posted question to me instead of putting them in the chat.
That's okay. That's what happened. I thought my chat had frozen.
Let me copy paste them in the chat.
Thank you. Yes, if you have questions, please address them to UNAM UK. That is the best way.
Okay, so I think these questions are for you then, Jorge. Can you see them in the chat? Or would you like to read them?
Yes, I see them, Mirko. Thank you very much. Well, it is a really hard question because actually satellite they need to be tested for, well, they need the thermal balance test. They have the thermium vacuum test. And so far, I'm not seeing the thermal shock test. Of course, all these tests are, remember that the satellite is moving around, for example, Earth, and the change in temperature is not so dramatical. So far as I know, the shock test is not required. And it depends, the number of cycles, it depends on the standard. For example, if you if you read the military standard, they establish that a complete cycle, and they recommend you to perform maybe like 3 or 4 times. If you want to run some thermal tests in, for example, for JAXA, it requires a number of tests that let me see, maybe like 16 or maybe like 20, because they want to run the thermal cycle over 1 month. So it's really a long test. And for the laboratory, we have the capabilities to run thermal tests at so far 1 week. However, we're trying to study if we can have a longer test, because as you know, these tests are really expensive. So far, yes, we have the scope, not for the thermal shock, only for thermal vacuum chamber, for thermal vacuum test. And not so far. We have the ISO, not the GX certification, and only for 1 laboratory. However, we're trying to aim to, for example, for other laboratories to be certified, to be, well, accredited. But as you know, this is not an easy task where we have that in mind. I know with this, we answered your questions.
Great, thank you, Jorge. Does anyone else have any questions for Jorge before we close today's session? Please speak now if so. And another one in the chat, if you can see that.
Yes, thank you
Fantastic.
so much. Yes, actually, yes, for example, the product that we have, it was to acquire tantalum. The tantalum was kind of difficult, was difficult to acquire, but it's more difficult to manufacture it. So instead of trying to construct the thruster with tantalum, we're using inox. So far, to use a different material can give you some idea of how the thruster will behave. And of course, when you introduce this in the vacuum chamber, they will last not so much or not so long as a tantalum thruster. However, it will give you a good idea. Of course, the data that we are trying to, the projection about we're trying to start again to manufacture the 3rd version, we're trying to do that next year. However, since we have already projects that we need to end, it depends of if we have the budget to start to start to buy the buying process of the elements, and also the manufacturing process. And also it depends of the money that we can have, since you know it's not cheap. But if you're more interested, I can share you my email, and we can talk about if you have some interest. If you're interested to have some initiative with us, and also we can share more details about our of propulsion tests.
Thank you, Jorge. Okay, so if nobody has any other questions, I'd like to thank you both again for taking the time to join the session today and to give such good presentations. And I'd like to hand over to Ana Elena to close things off. Have a great evening, those of you in the UK, and those of you in Mexico, and enjoy the rest of your day.
Thank you. Thank you very much. Well, it has been a fantastic experience to have academics from both universities sharing their experiences, sharing their knowledge and their resources together. We would love to continue this, to move ahead in other ways that we may be creative with. We would love to see more students from the University of Nottingham in future initiatives. So I think we may start thinking of ways in which this could be made to happen. Thank you to all of you who have joined us. Remember, those of you who have attended all of the lectures will be able to receive a certificate, which is something that Mexican universities do for attendance to this type of event. And we will be thanking, of course, participants with their own certificate attendance. We look forward to more collaborations with the University of Nottingham in this area or in other areas that we may detect that are suitable. UNAM is a very large university, as you know, and we would be very happy to discuss other options. And we send many greetings to Daphne Gaviria, who has been so important in order to make this happen, as well as to Shannon Baverstock, who was with us for the previous two occasions. Thank you very much, and we look forward to being in touch. Thank you, David, for chairing today's session, and to all of you. Goodbye.
Thank you. Goodbye, everyone.
Bye-bye.
Bye-bye.